Alright, so these are the class notes for 11.2. Today we're going to be talking about the properties of tangents. So just a refresher, a tangent line touches a circle at exactly one point, and a tangent segment is a line segment with a start and end, and one of those endpoints is on the circle. So today we're going to be talking about some of the properties that these tangent lines have. So first, if a line is tangent to a circle, then it is perpendicular to the radius drawn at the point of tangency. So if we have this line here, line L, and it touches the circle at point B, if we draw a radius from the center to B, then those have to be perpendicular. So if L is tangent to circle C at B, then line L is perpendicular to the segment CB. So this here is the symbol to say that it is perpendicular. It works the other way around as well. If line L is perpendicular to CB, then you know that line L has to be tangent to circle C at that point B, meaning that they have to form a right angle, the radius and the line of tangency. So example 1, if the ray AC is tangent to circle B at point C, then find BC. So if we know that this ray, AC, is tangent to the circle, then it means that the radius and the tangent line have to form a right angle. Now, we know that that forms a right angle. Look here and you can see that there is a triangle in here, and that is a right triangle. Since it is a right triangle, we know that the Pythagorean theorem must be true. So, a squared plus b squared has to equal c squared. And we can use this to solve for our missing side BC. I will plug in x squared plus 12 squared equals, my hypotenuse here is 13 squared. 12 squared is 144. 13 squared is 169. So to get x by itself, I subtract 144 from both sides and get x squared is equal to 25, meaning if I take the square root of both sides, x has to equal 5. So BC is equal to 5 here. Alright, example 2. How can we show that ray EF, or the line EF, must be tangent to the circle? Well, we know that if this line is tangent, it has to form a right angle with the radius. So if we can prove that that's a right angle, we prove it's tangent. How do we prove it's a right angle? Well, again, you can see that this forms a triangle. So if we can prove it's a right triangle, then that will prove it's a right angle. And to prove it is a right triangle, we want to see if the Pythagorean theorem, a squared plus b squared equals c squared, holds true. So what will we plug in? For a and b, we will plug in 9 and 12. And for c, we plug in for our hypotenuse 15. Will this be true? 9 squared is 81, plus 12 squared is 144, 15 squared is 225. 81 plus 144 is in fact 225. So the Pythagorean theorem is true, thus implying that it has to be a right triangle, meaning that that angle has to be a right angle, and therefore it must be tangent. Alright, we have another property about tangents. If we pick a point outside of a circle, so in the picture we pick this point here S, if two segments coming from the same point outside of the circle are tangent to the circle, then those lines are congruent. So if we pick our point S and we draw two lines going from S to the circle that are both tangent, so we have this line here, ST, which is tangent, and this line here, SR, which is tangent. If both of those are tangent lines, then it has to be true that they are congruent. So, in words, if SR and ST are tangent to circle P at points R and T, then SR must be congruent to segment ST. So in example 3, we're going to use this property. Both of these lines here are coming from point A. AB is tangent to circle C, and AD is tangent to circle C. That means by this property that they have to be the same. So we can set their lengths equal to each other. 2x plus 3 must equal 11. Subtract 3 from both sides. 2x equals 11 minus 3 is 8. Divide both sides by 2, and x has to be equal to 4. Alright, there are 3 checkpoints. I would like you to pause, try the checkpoints on your own, and then unpause to see how you did. Alright, unpause and see how you did. Did your answers match up with mine? On number 3, I care less about what form your answer is in, since I didn't specify, but I want to see that you plug this into the Pythagorean theorem. You could have left it at the square root of 274, or put it in your calculator to get 16.6. Right, last problem. A child is standing at a pool at point B, so here's point B, which is 2 feet from the edge of a wading pool. So the distance from the child to the edge of the pool here is 2 feet. The distance from point A to point B is 4 feet, which is given here. So down below it says if the radius r of the pool is 4 feet, is AB a tangent? So if we plug in for each of these r's a 4, how do we determine if that line is tangent? Well, if it is a tangent, this has to make a right angle. And if it makes a right angle, this makes a right triangle. And the Pythagorean theorem, a squared plus b squared, must be true. So we can plug in for our sides. A, I'm going to plug in this side here, 4 squared, plus for B, I'm going to plug in this side here, 4, equals, for C, I have to plug in my hypotenuse, which is 2 plus 4, so I do 6 squared. 4 squared is 16, so 16 plus 16 equals 36. 16 plus 16 is 32, so these are not equal, meaning that AB is not tangent to the circle. However, we want to find the radius r if it does form a tangent. We've seen here that it is very close. 32 and 36 are close, but they're not quite equal. So we want to try a number that is close to 4 and see if it will work. So I'm going to try what's close to 4 is 3. If I plug in 3 for my radius. If we try a radius of 3, so we're going to try that r equals 3. Then when we use Pythagorean theorem, we will have 3 squared plus 4 squared equals, and our hypotenuse will now be 3 plus 2, which is 5 squared. 3 squared is 9. 4 squared is 16 equals 5 squared, which is 25. 9 plus 16 does in fact give us 25. So 25 equals 25, so this will work. So to make this work, the radius has to be 3 feet.